Testing. Okay, good afternoon to everyone. So tonight is your project one due date. Okay, so I won't be have time going through all your draft anymore. So if you have last question, you can go to my office or later, and then you can fix it. And then you need to submit with your cover page. Do you see cover page in the Moodle? Okay, and then you need to submit to turn it in. You already sign in you to turn it in. You know? Okay, and then you submit together with your report. Okay, the report contains the highlighted part. So one thing I want to look for in your similarity is I don't want it to be like the whole sentence get highlighted. Okay, if you get a sentence get highlighted, make sure that you paraphrase it. Okay, paraphrase it. So don't keep submitting your turn-in checking because after 3 times, it will become longer and longer time to generate your report. Okay, so be sure after you submit once, then change it. If you have any turn-in problem, you can come and find me later. Okay, and then so after submission, right, I will hand it back to you to do correction. Okay, so you still can do correction. So that time, you can earn up to about extra 2 marks. Okay, after I mark, I hand it back. You should do correction. Okay, so maybe some of your project is pretty hard, right? Okay, so you talk with me and then how I help you to resolve it. So make sure you follow my resolution. Okay, so if you follow what I say, then can get better mark. Okay, if you don't do what I say, then it's hard to give you marks. Okay, so this is actually how it works in FIP. Okay, so FIP usually you can graduate with ease if you are okay. I mean, you do whatever your supervisor asks you to do. Okay, usually if you get back with your supervisor, then you will be graduated with good marks. Okay, so make sure you have a good relationship with your supervisor. Okay, so this project is training you how to write a proper document, max document. Okay. Hey, Yi by the way, you haven't submit your draft. 对，才做完。哦，draft 不一定要做完的，draft 就是大概你有什么，然后你自己去补充。OK，呀，如果你还要我看的话，就等一下，OK，等一下给我看。还有红杰有 draft 的吗？什么？啊，可以啊，可以先大概确认一下 content，然后你就装进去写文了。等一下可以见哦。还有吗？应该其他的都 OK 了，差不多。好，还有小杨，你是没有给我看 draft 对吗？啊，最怎么样？还有看吗？啊，什么？没什么，没写 draft，没写 draft，不是你有交 project 吗？还没交，要交吗？啊，不然呢？啊，今天，啊啊啊，今天交的是吧？交的就 OK OK， so we'll see how it goes. All right. Let's talk about a little bit on differentiation chapter first, and then we will go into integration today. Okay, so let's recall some important theorem in differentiation, and then we'll an idea, and then we'll go to integration today. Right. So one of the main thing in a differentiation chapter is the Claira's theorem. Okay, Claira's theorem. So what does Claira's theorem say then? Okay, if fxy, wait, that is the result, right? So y fx, when is it fxy equal to fyx? What is continuous? Huh? What is continuous? how do you make sure fx1 equals to fyx? What's the sufficient condition? Bombing. What's the sufficient condition here? What's the sufficient condition? What both is continuous? fxy and fyx are continuous. Continuous way on the open set. Okay, later we'll discuss about open set again. Okay. Well, I mean, if you think of this statement in one variable calculus, what does this theorem say? If you think of it as a one variable calculus here. If you make it into one variable calculus, what does it say here? If the second derivative is continuous, then second derivative equal to second derivative. Okay, so kind of trivial in first variable, correct? No? Because it's already continuous, right? Obviously, there's f prime prime there. But in two variable, it's different. Because in two variable, you can look at different direction when you do second derivative. Okay. Yeah. Okay, in one variable, it's trivial. But in two variable, it's a bit subtle. Okay, second, extreme value theorem. So what does the extreme value theorem says? If f is continuous on a closed and bounded set, then what? Then what? So this theorem got extreme value, right? So this extreme value belongs to who? Extreme value is this. F, right? Okay. So F will attain the maximum and minimum. So what kind of maximum and minimum? And absolute maximum and minimum. So there's also a one variable version of this extreme value theorem, right? So in one variable, f is required to be continuous on what? On a closed interval. Okay, a closed interval here. Okay, so closed interval obviously is finite. Sorry, bounded. Okay, now. Okay. So where can these absolute maximum and minimum exist? It could either exist in between A, B, or at A and at B. At A and B mean at the endpoint. Or last time we learned it called the boundary point, right? Okay, if you stand at A, if you form an open interval beside around A, you will have point inside this interval and not inside this. Okay. So I mean, whenever you see an interval, right, you should think of it as a real line. Okay, think of it as a real line. And then if you form a open interval, any open interval around A, if you move a little bit away, either you are outside the set or you're inside the set. So this form a boundary point. Okay, right. So there are some idea I want you have. So let's talk about this openness here. So let's talk about open this. Okay, so what's open this? So open this is written as del D with a radius center at AB, say. Okay, so what are these? These are all the points in R2 such that the length between the point and the center is strictly less than delta. Okay, strictly less than delta. So how do you imagine this point here? So you should imagine a dotted this here, the boundary. Okay. So can you think of a one dimensional um, version of this open disk? What is a one dimensional version of this? Sorry, 一条线，没有 endpoint. Okay, or in other words, so in R, we have open interval. So open interval, you should also think of it as a sitting on the real line here, but not including A and B. Okay. And then from here, remember last time, from here, we define what set is open. Okay. So we define that S is open if, so let's put it this way. So the set X is open if for every xy in X. So where is this X live in? This X should be a subset of R2. Okay. For every point inside this set here, there is a open disk. Okay. Let's center xy such that this open disk live inside. So I claim that this is similar to say why open interval AB is open. Okay. So there's also a one dimensional version of this openness here. So is it true that, for every point inside this open interval, you can find a smaller open interval that live inside this interval here? True. Let's say I give you a number x in between a, b. Can you find an open interval around x that live inside this open interval a, b? So let me draw this picture. So now I think it's a very useful tool. Whenever you see this inequality, right, try to draw it on real line. So you have a, you have b, and then x in the middle. So how do you find an open interval around x that live inside the open interval a? What do you think? What do you think? You know what I'm asking or not? Who say no? 认同啊? Which sentence you don't know what I'm saying? Can you repeat what I say? So you need to listen first. You need to capture my sentence first before understanding. If you cannot capture my sentence, you cannot understand. Okay? So make sure you capture my question first. Okay, before you understand what I want to do. So my question is, you find a for any point in between A, B, okay, can you find an open interval that contain X and live inside the open interval of A, B? Sorry? Sorry? 找到两个？啊哈？什么？你在问我还是你在回答我？你在回答我。I want to find an open interval that contain X and contain in A, B. Open interval A, B. Can you find an open interval that contain X or not? Sorry? A 加 X 3. Oh, okay. And then x 加 b 3. Okay. So you mean you find these and this midpoint, right? So midpoint between ax and xb. Okay. Yeah. But I mean, you can easily take AB, right? Also can. Does it make sense? You look at AB. Right? So X is in AB. AB is obviously you can take what Xiao Peng say. You can take the midpoint. Okay. Between the left endpoint and X and the right endpoint and X. Also. Okay now. So this openness actually is really generalizing what we have in the one-dimensional case. Okay, it's trying to generalize what we have in the one-dimensional case. Okay. Okay. 哎，苍蝇，你的 draft project one 交了吗？要交吗？哦，直接交哈，你要直接交。哦，今晚交啊。OK，好，OK，any other question you want to ask or anything about your assignment you want to ask related to this chapter? You try look at the assignment question yet? Not yet. Yeah, try to read it first, even though you don't do it. Try to think about idea first. Don't left until last minute. Last minute doesn't work here. Okay, so make sure you read it first. Even you don't do it, read it first. You will think about ideas. Okay. Okay. Yeah, don't left everything to last minute. Okay. So let's start with integration now, multiple integration. But let's quickly say what's about integration first. So where do we start integration? Like how about Riemann, Sama, and all those things? Where do we start with? What do you think? We don't start with a sign of integration. Okay. So how they think about this integration was, it's very simple. It's very simple from high school. What do you learn? Okay, the first thing you learn is, no, so not high school, just primary school. Area of rectangle. Okay, how to compute area of a rectangle. So you have a rectangle like this, and then you just take, what do you take? Length side width. Okay, length side width. Okay, so we are trying to use this rectangle to find what? The area under the graph. Okay, so we're trying to use this rectangle to find the area under the graph. So how do we use a rectangle to compute area under the graph? Okay, so we try to put, you can imagine like a sellotape. Okay, put a few sellotape below the graph. Sellotape below the graph. And then you just take off all the sellotape and then compute the area. But you found that there's a problem actually. You see what's the problem? Can you see what's the problem? If I just take this sellotape and then compute the area under the graph. You see any problem here? You see any problem? What's the problem? 不长. So I didn't really fill all the area under the curve graph, right? So in particular, this part here. Okay. So what can I do? What can I do? Cannot. Still got stuff haven't been filled yet. So what should I do? I should take a selected with smaller width. Okay. Try if I take a smaller width, what can you see here? Let's take half of it. Can you see that I can fill in more empty spaces here? You see that I fill in more empty spaces here? Okay. So integration is about taking smaller and smaller telephone tape to fill out the area under the graph. Okay, to fill out area under the graph. Does it make sense? Okay. So I mean in two variable case, okay, in the function of two variable case, instead of using just rectangle, we will use a volume of what? Okay, instead of using rectangle, we will use cuboid to fill out the space under the graph of function of two variables. So let's draw the cuboid here. Okay, so you have a, let's say, a mountain. Let's say you have a mountain. Okay, so how do you compute? We call it area. I think we shouldn't call it area now. So we just call it volume. Okay, let's call it volume under this graph here. Okay, so how do you compute it? So you put a bunch of cuboid, okay, under this graph here. Okay. Yeah. Can you imagine? Can you imagine? So if I put smaller and smaller cuboid, I can fill out the empty spaces. Okay. I will show you a more better picture later. But do you ever ask why area is a width times length? 什么？没有问过。为什么要拿来乘呢？要不要拿来加、拿来除啊，还是再乘一些其他东西？乘 why? Why we call this an area? Yeah. Okay. 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 Kind of makes sense. Kind of makes sense. 懂 Isaac 在这种 kind of makes sense. Okay. Yeah. Yeah, you should think about it. Why is this called an area? Okay. All right. So let's look at this. So we really start with one variable first. Okay, so what do we do here? How to read this? How to read this notation? This notation is what I said just now. It's just that we put into a mathematical expression. How to read it as a rectangle here? Can you find rectangle here inside this expression here? Where's the rectangle? Where's the rectangle inside this expression here? The linear expression here. Which part is the rectangle? FSI times delta x. So delta x is the width, and then f is the length. Okay, so n represent how many rectangle gonna add up. What is this limit here? What is n to infinity? Put the same n. No, so here would means that you will take smaller and smaller width actually. Okay, so meaning you take smaller and smaller telephone tag here. Okay, so that your number of partition will increase. Okay, now understand? So two things you need to remember in the integration. One is rectangle, second is smaller rectangle. So here is it. Here it is. So here is rectangle. Here is smaller rectangle. So that's why you have a limit and sum here. You need to sum all the rectangle together. Okay? Okay, can remember or not? Integration definition. Two things you need to remember. One is rectangle, one is smaller. Rectangle is fx times delta x. Smaller is the limit part. Okay? Never forget that. Okay, let's go on. So next, to talk about volume under the function of two variables, let's start with a rectangle first. Okay, so let's start with this R, where this R is controlled by what? X is controlled by A and B, and then Y coordinate is controlled by C and D. So your R is in the middle. Okay, so what can you do is you can split AB into M subinterval and CD into N subinterval. So you see, what we do in the two variable case is a double up job. Okay, in one variable. In one variable, you just split one interval into few subinterval. But now you need to split in two directions. Okay, two variable is split in two directions. Three variable you split in three directions. Okay, so in general, n variable you split in n direction. So if you split AB into M equals subinterval, CD equal into n subinterval, then you will split R into M times n subinterval again. Okay, so you should imagine the picture like this. Okay. So whenever you see this kind of construction, right, try and draw it up. Okay, try and draw it up so that it will make sense to you. I would prefer that you will learn this better first, then you write the word. Instead of writing word and then draw this. Okay, so you need to understand the idea first, and then you will write this. Because this doesn't matter how you write it. Okay, as long as you explain the things right. Okay, doesn't matter how you write it. Okay. Okay. So after this, what do you do? So after this, we will do something similar as what we did in Riemann sum there. So in the one variable case. So what we do here is we take delta A instead. So what's the delta A here? So delta A is the area of the small, what do we call it? Small subrectangle just now. Okay. And then we have the height. Okay. Height, what is height here? Height is f of some point inside this subrectangle here. Okay. So together, what is this? Area times height. What do you get? You get a volume. Okay. So what volume is this? This is a volume of cuboid. Okay. Volume of cuboid. Okay. So why sum over m, sum over n? So you need to sum over x variable. You need to sum over y variable. Okay. Okay. So there are two sum here. So you need to sum across here, and then you need to sum all of them together. So there are two directions to sum here. Okay. Okay. So what to do? You can see that if I'm gonna estimate what is the volume below this surface here, you will put a bunch of cuboid. Okay. But can you see that this cuboid is just trying to estimate this surface? Because this cuboid is not smooth. It's not smooth. Okay, it's not smooth. So to make this cuboid surface smooth, what do you need to do? You need to take the limit. Okay, what's the limit here? You will cut R into smaller and smaller subrectangle. Okay, so you should imagine that in the double integral, how do we define it? We define as a doubly limit on doubly sum. Okay, because you have two directions to add up. So there's a doubly sum and a doubly limit. Okay, so you need to cut infinitely times in one direction, in x direction, you also need to cut in y direction. Only then your cuboid will become smaller, smaller, and smaller. Okay, does it make sense? Okay. Right. Okay. Remember the last time I mentioned about this limit thing? Because if you take limit to infinity, right, you should imagine that your delta A become 0. So if your delta is 0, you just add up with a bunch of height times 0. Shouldn't you get 0? But it turns out that this limit will compute to something useful, some finite number. It's not always 0. You understand? You understand? Okay. If we take limit, right, to 0, potentially, I mean, this delta A should go to 0, right? But turns out that the limit will compute to something useful, something finite, not always 0. You know? Yeah, that's why we study this kind of limit. Yeah, otherwise it's useless to define. Okay, so if we look at limit, doubly limit of doubly sum here of cuboid, we define it as a double integral here. Yeah. So whenever you see a double integral of function of two variables, okay, and then dA is what? Is a doubly limit of doubly sum. Okay. So why doubly limit of doubly sum? You need to cut in two directions. Okay, make the cuboid smaller and smaller. So imagine if you have a cuboid, you just cut in one direction, your cuboid will become long, right? Does it make sense? So you need to cut in the other direction also, okay, to make the cuboid small. Okay, so there's some so like what I told you, in this class, we don't really play around with definition too much. So we need to tell you some tool to compute the integral here, double integral here. So first thing is, if you know that your function is always positive, okay, then this double integral here will represent the volume, okay, volume of solid under the surface. So this is similar to the one variable case. Okay, if your function is positive, what's the integral of that function? It's just the area under the graph. So it's similar. So let's look at this case here, this example. Let's try to evaluate this function here on a rectangle region. Okay, rectangle region. This is not quite rectangle. Is it a rectangle? Yeah, it is a rectangle. So one side is length 4, the other side is length 2. So look at this function here. You need to ask yourself, is this a function positive function or non-negative? Is it non-negative? Okay, so square root always give you non-negative number here. So how to compute this? You need to compute it as you can compute it as a volume. Okay, so you no need to use this definition here. No need. Okay, so if it's greater or equal to 0 for this function, you just compute the volume under this surface. But can you draw this surface? What's this surface? Do you still remember? What's this surface here? How to find this surface? So let's recall what you have learned before. Fx y equals to square root 1 minus x squared. What is this graph here? This graph. Huh? Cylinder. A cylinder? So how do you draw it? How do you how do you get cylinder? Uh-huh. Okay, well, I mean, so okay, so let's try, let's work it out. Let's recall what you have learned before. So if you fix a y, what do you see? You see square root y minus x squared. But how to graph this? How to graph this? Square root y minus x squared. So this function, how to graph it? So let's try. What's the axis I should put here better? One side is x, one side is z. Anyone has objection or not? Why we should z, not y? Can ask, now is the time for you to learn, for you to make mistake. Exam mistake, you deduct marks. Here, make mistake, okay. Okay, so if you're going to make mistake here. Okay, so why we don't choose Z over Y? Jason. Huh? Right, correct. Height. So this function should give you the height. Okay, so it's the z-axis. So if you have this two variable function here, do you know how to draw? Square root y minus x squared. How to draw it? Half circle. Half circle. Why is it half circle? Last time we talked about there's a full circle. We can describe as x squared plus y squared equals to 1. And then if you solve y in terms of x, you will find upper circle and lower circle. And then this is the upper part, plus square root 1 minus x squared. But remember, what this graph is only one slice of y. So if you look at different size of y, so for example, y equals to 0.5, y equals to -1, you still get the same upper circle here. So, meaning to form the graph of fxy, you just need to put all these slices of y together. Okay, so this slice is y equals to 1. So when y equals to -1, you also get the same upper cylinder here. And then similarly for all different y, you get the same upper circle. So if you join all the upper circle together, you will get the half cylinder. Okay. Okay or not? Make sense? Okay, man. Okay, man. So this is very important. This slice is very important because later when we learn vector calculus, we're gonna slice our surface up like this. Here we look at a particular y or particular x or particular z. So it's very important to form how to form this half cylinder just using upper circle here. Okay. Right. So right. So can I give you 1 minute and think about how to compute a volume of this half cylinder? You 1 minute. Okay. So I mean this cylinder should be infinite, right? But what we care is only around the R. Where's the R? R is going from -1 to 1 and -2 to 2. So do you know that which coordinate here refers to x, which coordinate here refers to y? Okay, usually the first one will start with x, and then second will start with y, and then z, and so on. Okay? So -1, 1 is about x, okay, and then -2, 2 is about y here. Okay, so you have these, let's say this part here. Okay. Right, how to compute this volume? Isaac. Yeah, use cylinder, sure. So what's the formula for the volume of the cylinder? Hmm? R square. And the height, okay. Uh, Wait, height is the y-axis? You sure? Okay, yeah, I think so. Okay, so what's the height? What's the height? What's the height? 2 minus negative 2, good. What's the radius? Okay, radius is 1.
Uh, this one is the half cylinder, so we need to
Divide by
divide by
2. Okay, good. Okay, so did all of you get 2 pi or not? 2 pi? Okay. Yeah. Okay, I get 2 pi. Good. So this is one way to see double integral. I think this is also how you teach integral in China, is it? 是不是？我问过中国的学生，他们怎么教积分？你们学积分是不是用一些 area 来计算？有吗？有学过吗？你们可能打有吗？怎么学啊？中国积分 integration？你们有学 integrate x 等于 x square 除2吗？高中教哪一个？啊，教面积对不对？Yeah, yeah. So this is similar to what you've done before. Okay, we first teach you how to relate double integral to volume first. Okay, then later we'll learn different way to compute it. Okay. Okay. Let's do one more exercise and then we'll go to next year. Okay, let's try and compute this. So we have this function here. So this function is a step function. Okay, why is it a step function here? I mean, it's a step function in 2 variables, so they call it a staircase function. Okay, so how to see these? This is like piecewise. But piecewise here got 2 variables because your domain here, 2 direction here. So if you look at S going from 0 to 3 for 3 cases, so let's pull out where is 0, where is 3. Okay. And then you can see that the difference between these 3 piecewise part, right, is the y variable here, is the y variable here. So when it is y going from 0 to 1, the height is 1. Okay, when the y going from 1 to 2, the height is 2. Okay, so you can see that when y increases, the height also increase. Yeah. All right. So now you are asked to compute the double integral of this surface here. So you can see that this surface here is always greater or equal to 0. So meaning what? To compute this double integral is to compute the volume under the surface. But can you see what this volume under the surface is? What is it? What is it? Huh? What is it? 号码是什么东西？长得像什么？ What does it look like? Cuboid, right? So it's a bunch of cuboid. How many cuboid? 1, 2, 3. 3 cuboid. Okay, so try and compute the volume of this 3 cuboid, and then we can compare. I give you 2 minutes. Try and compute the cuboid. Okay, so let's see. Okay, so what's the formula for the first volume of cuboid? Volume of the first cuboid. What's the first one? How do you split that up? Do you split out like this? R1, R2, and R3. Okay, so what's the volume of R1? 1. Okay, and then volume of R2? 3 times, 2 times, 1. So it's just changing in the, in this case, we call it higher. And then 3 times, 3 times 1. So what do you get? You get, okay, no? Okay. Yeah. Yeah. So far, okay. So this is the basic. Okay, so let's finish out with this theorem here. So if you can see that if f is bounded on the closed rectangle here, so in our case here, you can see that our function is bounded, okay, in the closed rectangle here. And also, okay, if it is continuous except at finitely number of smooth curve, what does it mean? So you can see that this function actually is not continuous. Not continuous, right? Because if you look at this, where is this? Y equals to 1, y equals to 2. Okay, you can see that the left limit and the right limit is different. Okay, so it's actually not continuous, but somehow we still can compute the volume. Why? So this is allowed. Okay, it is allowed at finite number of smooth curve. So in this case here, where is the smooth curve? So the smooth curve is actually what? Actually when y equals to 1 and y equals to 2. Okay, so the smooth curve live down here. So let me draw it. So y equals to 1 and y equals to 2. Okay, finally number of smooth curves here. Smooth curve. Then f is still integrable. Okay, if f is continuous, then it is integrable. This is the same as what you know in calculus 1. But even I talk about this continuous except on finite number of smooth curves, right? There's a version of one variable calculus also. You also allow discontinuity at finitely many points. Okay, finitely many points. I can ask a question that do you know how to compute the area under this round? Okay, it's the same area under the curve. Okay, although this point is omitted, it's fine. Okay, actually, it's the same area. And so finitely only. Okay, if you take off too many, then there will be a problem. Okay, but finitely many is still okay. Okay, and double integral also have nice property like the one variable case where you can take scalar out. Okay, you can take the scalar out, and if you integrate some, you can split out the integral. And if you know that one function is smaller than the other function, then the integral is always smaller or equal to the larger one. Okay, yeah. So this one, two property, right? What do we call it? We can pull scalar out, we can split sum. What does it call? Linear. Okay, so this means that this double integral is a linear operator. Okay, linear is linear. Okay, scalar out, you can split sum. Also, it respect the order. I respect the order. Respect, right? Because follow the same order that it takes on function. Okay, so it respects order. Okay. Any question? Any question before we take a break? So there's a question by Ling. I haven't had time help you to see it yet. So maybe next time, next class. And the other question, I think by Boom Ping. So Boom Ping asked me whether there's a set that is open, open and closed, open and closed. So you can get all composition. You can get open and closed set, both open and closed, open but not closed, closed but not open, and not open and not closed. Okay, you can get all these cases. You manage to find an example or not? So what's an example that's open and closed set? Okay, yeah. Okay, empty set is both closed and open. Okay, huh? This one only. Yeah, you can try and find the other. So for example, right, why open set is open and closed? Try and prove it. Mm, so well, I mean, if you look at the example that we had last time, so this set that is not closed but open, okay, open but not closed. Um, this one closed but not open, or not closed but not open. Because if you pick one point at the boundary, any ball you make around that boundary point, it won't live inside the set. Okay. But which one is not open and not closed? This one, not open and not closed. Why? Not closed because doesn't have all the boundary. Why is it not open? Because there's a partial boundary here. So if you pick this boundary point, you form a ball, it won't get into the set. And because the ball must contain something inside and outside. So this is not open and not closed. So all the condition, all the possible combination, you can get an example. Okay. Yeah. I mean, another example for open and closed set is the whole space R2. It is closed and open. Okay, open is easy because any ball should live inside R2 because R2 is everything. But why is it closed? Yeah. Or in other words, you can use another definition, right? You write R2 as a R2, take away some open set. But you prove that open empty set is open. So R2 can be written as R2 take away an open set which is empty set. Okay, if you prove that empty set is open. Okay, so for this open business, closed business, bounded business, I only need you to require you to play around definition and then give some example. That's all. Okay, no theorem on them. Okay. Yeah, you should at least know their examples and then how to prove their examples. Okay. Or they satisfy the examples, satisfy the definition. I think one very interesting phenomenon I saw in your project, you will write something, right? Rigorous definition, precise definition like that. Uh, I mean, well, it's normal for you because you just first time seeing this. But I hope when you get along with a mathematics degree, you should think that this definition is actually the actual definition for limits, integration, or differentiation. It's not precise. It's not rigorous. It is the definition. OK，它就是那个 definition，它不是什么很 rigorous 的，它就是那个 definition。You get what I mean? Yeah. So meaning I want you to take this definition or so-called the rigorous definition as a natural definition，自然的一个东西，对你来说已经是自然的。OK，以前不自然很正常，but when you go along with this degree, you should take it as a natural definition，自然的东西。啊，OK，OK。All right, so let's take a break until 2:08. 哦，你知道我在这边
我看到对，我肯定
看到了，我飞着我。
好了。induction 好像，好像不用 induction 呢。
怎么？
这个是就是我要 prove 那个 disjoint cycle 那个东西。
嗯哼，
然后这个我觉得不用看，我觉得看这个就可以了。就是他讲，我讲嘛，如果我给你一个这个 permutation of 这个它是这样子的，这个是一个的情况啊，你只有一个那个 disjoint cycle。
哦，OK，
然后如果它的这一个长这样子，这个 notation 我应该会换啊，我应该会换方块。然后它就你拿 standard closure 的话，你拿 standard closure 的话，我们就会 connect 这个，因为它的这个我们就你第一个嘛，如果这是一二三的话，第一个的 starting point 需要第二个 ending point，第二个 starting point 会需要第三个 ending point，所以你的那个 standard closure 就会 connect 第二个 ending point 跟第二个 starting point，然后我就这样写哦，然后最后一个就是到这一边，要这样，到这一个的时候，这个的
要
如果
接回来
对借回头，然后就有这些东西了，所以这个东西 form 一个 element 哦，一
，component，
个 component 啊，
嗯，
所以它就减少了k 减一个那个 component 哦，of standard closure，因为它自己 form 一个嘛，原本这 k 条如果是直线的话，它们就会是 k 个 component，可是你把这 k 条都接起来了，所以它就变成了一个 component，代表你原本有 k 的，然后你变成一个，所以你少了 k 减一个东西。
哦
嗯，
，OK，OK，OK，OK，
然后呃，这个就是讲一个 cycle，然后就讲他们乘起来的情况，因为他们是 disjoint，所以呃，involve 在一个 cycle 里面的 starting point 跟 ending point 是不会在另外
嗯哼，
一个那个叫什么 cycle 里面出现的。
嗯哼，
所以这些分别，i 个他们都会 form i 个呃，分别会 form i 个 component，
嗯哼，
然后 form 了 i 个 component 之后，你要看他们的那个 length 是多少哦，我 denote 他们的 length 是ai 啦，这样子你
哦，
的
我知道了，你是从那个全部的直线开始看，and
嗯，
then 你就如果
如果有一个
中间
cycle，
有三个，
有一个 cycle
你就
罢了，对，
把它们
这些全部就全部线会
对啊
连起来
在一起，
变成一个，
对，
然后它就少了 k 减一个东西哦。然后如果我有多个赛克，而且是 d
就
i
一
赛克，
直减。
对，就一直在减。然后他们的
可以减一那个 E 是因为那一
它
个
也会放一个嘛，
KI
它不是全部 k 不见掉，放一个它还是有一个很可能在。
呀减了 K 再加一这样，
对对对啊，减 k 加一就是减 k 加
呀
一，然后
减 K 加
你把它放成减 k 减一这样子哦，一个刮胡这样嘛。对，然后
，OK，我觉得 make sense，
是我觉得这样，
我觉得
对我应
make
该
sense，
会写这个应该是玩哪一个 pro induction。对，不
yeah，
过如果要用到这一个方式来讲的话，我就要讲那个natural inclusion of Bn to Sn 哦，
讲讲，
因为我要用 Sn 里面的property 嘛，所以我要
哦
讲这个 Bn 它其实 satisfy Sn 的 property，natural inclusion 过去里面。
等一下，你这 natural inclusion 会不会看漏东西啊？
就是谁是 subset 的问题哦，这个是应该是 Bn 是 subset，
因为你知道为什么吗？因为
要看你怎样 define 你的那个 function 吧。
等一下我想一下啊，你
嗯，
这个 I mean，还是啊，这个是记忆式的，是不是？嗯，
还是我自己 define 一个 map
不是，我现在的问题是你的 break，
relation 的问题。
我想一下，因为有一个问题，如果你没进那个，
去不
对，你没进 symmetry group 有一个问题，就是如果你 map sigma i 进到 symmetry group 的话，它们会变成 identity，
可是
但是你
哦，
是不要它变成 identity 的，
不要它变成
你不要啊，
我 natural
因
inclusion
为因为因为你做 CMI 2次的话会做出什么？
是，它会这样子，然后这样子，然后再这样子，然后那个东西会转回在这边，所以那个一它原本去了
哦，
二，
确实哈、
啊，所以它会
哎，
变，
这样你要解释一下，因为
是，
不 trivial 这个
对对，
东西，
我会解释，就是
因为 Sigma I 的 Sigma I compose 过后是 identity，
其实我原本想要这样子 define 这个东西，
不是我的问题是这个，
对，你要写一下，
问题是这个，就是如果你这样交换，
在这个再过回来，yes，这样子，
然后你 standard word closure 嘛，确实是 two component 嘛，但是哦，如果你用你的 inclusion map 去那个 symmetric group 啊，你这边是斩将的，你知道吗？
因为我们是看 permutation 嘛，
我知道，我知道，
所以
我知道，
所以
但是 permutation 过后是
这个也是没有问题啊，因
identity 啊，
为他们还是两个
我
component，
知道，但是它的两个的原因不同啊，I mean 是原因不同，
他们两个的原因不
就
同，
原因不同，
因为他们
因为头跟头
因为
接不了，
他们的那个
头跟头
permutation 的关系，所以我到最后只看
我想想，
permutation 了。我觉得这个也是要解释，确实也是需要解释的。
我想想，
嗯，我们到最后是看这个线的
因为你对
结束点，因为什么？因为这个
线的结束点，
线的结束点，我们
我想一下。
不是看它线的中间。
现在你要讲好这个东西，因为为什么？因为这个，因为你要解释完全部这些东西，不是？但是这个 map 其实是不 injective 的，
对，所以我只是讲 natural inclusion，我不会讲它是 injective，不可能是 injective，
没有 include 啊，不是 inclusion 啊，它
不是
是一个
inclusion
像 projection 啊，应该，
projection 啊，
因为对啊 project 嘛，因为你的那个 crossing 不见掉嘛。
中心不见掉了，对
然后
projection。
I mean 我的意思是说，对，你要讲这个为什么看这个可以看这个，你要讲那个
哦，
endpoint 的问题，不
为什
然的
么我可以
话，
只看 endpoint，我不用看中，我可以不理中间的东西吧？
嗯，
可是我刚刚那 cycle 不算是在解释这个东西吗？
因为你 cycle 是活在这边的东西。
哦
不是这边的东
哦，
西。
对
虽然那个 cycle 确实会帮你记这个，
对，
我想一下啊，
可能
如果你拿 inverse 呢
没有啊，它 natural inclusion 不是讲 inclusion，就是你 project 进去的话，它不是一个 one to one 的 map 你
哦，inverse 也 OK，inverse 也 OK，你知道吗？
哦，你这样子画的话是 identity 啊，
诶，
你可能这个要盖起来。可是 check 过啊，我就 check 过很多次啊，就是我就 check 这个呃
没有，是说
cycle，
有些东西你要，
就是里面这些东西，我知道，就
嗯，
可能要讲类似于就是
我想一下，
为什么我可以变成去看 cycle，然后
对对
我可以不用
对对对
理它中间的那
对对对对
个东西
对
存在。
对对对，
这我觉得也是要讲好这个，要不然的话会 miss 掉一些东西，感
嗯，
觉很像不细节那种。
对对
，OK，
这个啊
这样的
这个版就这样子
哦，
，OK，拜拜。Okay, okay, let's continue. So let's continue with a second tool. Okay, we need to learn how to compute double integration. By the way, this Friday there's a replacement. And so there's a Christmas replacement from 1 to 4. From 1 to 4. Where's the place? Where's the classroom for Friday? Okay, for digital system. Try and check. Okay, so remember the differentiation chapter. What's the first thing we learn before differentiation? Before the tangent plane? What do we learn? The the del thing. What's the del thing? The partial derivative. Okay, so similarly here, we will learn what is called a partial integration. Okay, so we will do partial integration first. The integration. So suppose f is a function of two variable that is integrable. Okay, integrable on a rectangle. Okay, so let's put a rectangle first. Then we will define what is integration from C to D, okay, of fxy on dy. Okay, in principle, this doesn't make sense. Okay, in principle, this doesn't make sense. Why? There are two variables here, but you only integrate with y variable. So what happened to x variable here? What happened to the x variable here? Huh? A new function. We keep x as a constant. Okay, we keep x as a constant. You should imagine x is a number already substituted. Okay, so two, we define this partial integration as integrating the function fxy, okay, with respect to y from C to D by holding x constant. So you should imagine that as a sum constant. So it's like what you do in partial derivative, right? You want to partial differentiate with respect to x, you need to keep your y constant. So it's the same. Okay, it's the same. So how are we gonna use this? So if we gonna okay, maybe tell you the Fubini first. So if we're gonna integrate a function, so this you see if you see this kind of statement this is not rigorous. Tell me why is it not rigorous? Statement got problem. You should tell me why. In particular, which symbol doesn't tell you? ABC OK 啦 ，this one OK。I mean this one 我还可以放过它啦。之前大概有讲了，因为这些东西是活在 R2 嘛，所以 ABCD should leave it 把有一个是犯罪 function，要怎样的 function？好像课本只要 continuous 吧，不行的。OK， so F is continuous. Why? Because continuous on a closed bounded interval already. So you must achieve maximum and minimum. So already bounded. You understand what I say? So if you have a continuous function on a closed and bounded set, what does extreme value theorem tells you? 3个小时. What does extreme value tell you? F will attain the maximum and minimum. So it's bounded. So it follows from the continuity of closed and bounded interval. So I don't need to add extra bounded thing. Okay, obviously we need add bounded, otherwise this will compute to infinity. Okay. So how to compute this? We can use two partial integration here. Okay, so you can either partial integrate with respect to x first and then with respect to y, or you can do y first and then with respect to s. And then this kind of integral is what we call the iterated integral. Okay, iterated. Okay, 先做一个再做一个 iterated, iterative. Okay or not? So the main thing about this Fubini here is this one. This double integral doesn't depend on the order you integrate. You can do it on x and then do it on y, or you can do it on y and do it on x. But this is limited to a domain that is rectangular. Okay, so let's try. Should we try? Okay, let's try calculation first, and then I will recap. the concept again. Okay, let's try and do this. See if you can do or not without telling you what to do. I give you try 2 minutes.
Mm.
Okay, so let's see. Okay, so let's do the first one. So first, okay, so there's an irony thing here. Can you see some irony thing here? So whenever we put dx inside, actually we are doing the integral of dx first. So we do from inside to outside. Okay, it's not from outside to inside. Okay, 从里面做到外面。Okay, so if you want to integrate with respect to x, what do? We treat y as a constant. So we get x cubed y over 3 integrate from 1 to 2 dy. Okay, so what's this? So this is just n over 3y minus 1 over 3y dy, which is integrating from 0, 3, 7 over 3y dy. Okay, so what do you get? 7 over 6y squared, 0 to 3, which is just 21 over. Do you all get this? Okay, yeah. So how about the other direction? Maybe just straight away tell me the answer. Let's see if it's correct. What do you get? Answer you get? 3 over 2 also. Okay. So you should compute that they compute to the same integral. Why? Because what's the domain you are integrating over? Is a rectangle. Okay, so what's this rectangle here? So 1 to 2 on the x side, and then on the y side from 0 to 3. Okay. And then this function is continuous on the rectangle. Continuous on the. This is a polynomial function. Okay, so it's continuous. Okay, so they should coincide, no matter how you integrate, which order you integrate. But what is the meaning of integrating x first and then integrating y and then integrating y and then x? What's the meaning? So if you choose to integrate along x means what? You fix y direction first. Okay, once you fix the y direction, you will get a function of one variable. And then you are just integrating the area under this function here. Okay, so you are integrating a slice of y. And then what do? You integrating along the y. So you add up all the slices together to form the whole volume. Okay, so why the order doesn't change? So if you fix along x direction, okay, you get another one variable function. And then when you integrate, you get an area under this function here. And then if you add up all the S slices, is the whole function that you need. I mean, whole volume that you need. Okay. Okay. So changing order is just a different way to slice your, let's say, solid. Okay, solid in this case. Okay. So your graph of your function is a surface. But what's under the surface is the solid. Everything under the surface. Okay, can you imagine like this? Okay. Okay. So how about do this question then? Okay, try to do this. I don't want to tell you which order you want to do. You can pick any one and then do it. I give you 2 minutes. Pick any order you like. Because this is a rectangle, right? Okay. And then is it continuous on the rectangle or not? Polynomial function, sine function, and they are all continuous. And composite of continuous function is continuous. Okay, so you can use Fubini here. Any direction you can pick. Okay. Try different direction. See which one you like. Okay. Okay, anyone do dy dx or not? Anyone do dy dx? 有人做 dy dx 吗？没有。哎，怎么你知道没有人做呢？你只在做你自己的东西，怎么你知道别人没有做？嗯，没有。有没有人做 dy dx？order of dy dx？有人做 dy 是吗？有吗？没有吧？全部做 dx dy？你们班这么团结的？Okay, let's do dx dy first. Okay, dx dy 还是 dy dx？dx dy，dx dy。Okay. So what's the first integral here? You treat y as a constant and then you do integral over x. So what do you get? Negative y cos xy over dy. Okay, and then what do you get? Yeah, sure away, compute it, see if you get the same integral or not. Okay, do you get 0? 0, okay, good. Okay. So what does it mean as 0 here? Nothing. No volume. And why is there no volume here? So you can see that if you graph it out, there's a negative part for this surface here. Okay, so there's a negative part in this surface. So it is the same as a variable of calculus one of one variable, that the area under the curve cancel with the area above the curve. So this is the volume below the graph and then volume above the curve. Okay, so actually they can cancel in this case. Okay, so they cancel. Can I ask why people choose over dx, dy over dy dx? Oh, because you need to do what? If you do y first, what do you need to do? Partial integration. Or by parts, yeah. Okay. So I mean, for this kind of question, you need to try a lot and then try to see which order is easier to do. Okay, so that you don't get stuck in the exam. Okay, ma. Try and see different example inside your tutorial. And also there's a chapter and review question, right? So try and practice to see which integration which order you can do faster. Okay, maybe one is better than the other. Okay. Yeah, I think so far okay. So let's continue first. So this one I just left as an exercise. Okay, if you cannot do it, you can message me and then we can do it together. So this is just finding a volume of a solid under the surface over rectangle. Okay, so you can use Fubini here. Okay, you can use Fubini here. Well, I mean, although the picture is drawn nicely here, maybe it's a good exercise to show why this function is greater than zero. Okay. Yeah. If you're gonna calculate this using a volume way, okay, you need to show it. You know what I mean? 我讲什么东西？如果你要把这个当做的体积来算 volume，what do you need to do? You need to show that the surface is always greater or equal to zero. Yeah. Although there's a picture showing you, actually you should practice how to draw this picture. Okay, how to draw this picture. Potentially you need to draw it. Yeah. Do you know how to draw? 绘画嘛？绘画。因为这一个方向好像不是正常看过的方向，会绘画。绘画怎么画一个？Okay, so you look at this side. You look at the height slice. Yeah, sure. Okay, sure you can do that. Or you can use the method I teach you, the directional derivative. Okay, you look at what's the directional derivative along x, along y, also can. Okay, if you look at level curve, then you are slicing like this. If you look at directional derivative, you look at the function, the surface in x direction and in y direction. Okay, so if you see this curve like this, right? Can you imagine what's the directional derivative along x? Curving like this. What are you hoping? Who's it? Negative? Negative. What do you mean by negative? I mean the derivative. Derivative. Yeah, partial f to partial x, yeah. Y equal to partial f partial x. Is it? Is it? Why? So it's like how to say it's like a negative x squared, right? Okay, so if you partial differentiate negative x squared, you should get negative 2x. Yeah, something like that. Okay, no? Yeah, so if you see negative 2x, your curve should like curve downwards. So I mean, if you compute the partial derivative along x, you should see your gradient decrease when x increase. Okay. Okay, yeah. So either you use fx, fy to compute, or you can do what Isaac says. You can use a level curve. I'm not sure level curve in this case useful or not. I'm not sure. But if you do fx, fy, you can see how the surface get curved. Correct or not? Because what is fx? Fx is the tangent of the intersection between what? Between the surface and the z-x plane, center at the point you want to see. So you can curve out this curve here. Okay, so fx, by computing fx, you can see in this direction what curve is it. Okay, if it is fy, you look at this direction. Okay, but what Isaac said just now was looking at z direction. So you see, you can see it in three directions actually. And so you can see these things in three directions. So can you draw the picture out with this three directional? Okay, it's kind of important. Correct? 对吗？那个谁啊？我不会骑哈。你的 project 是不是 Lima Beam curve 啊？是不是用 horizontal vertical tangent 把那个 curve 画出来 ？Similar in this case, this is a three-dimensional case, right? Three-dimensional case. So you can use fx, fy, and then draw your surface on. Okay? Okay, one-dimensional vector. Okay, so continue. Okay, try. Make sure you try this homework question. Okay, if you cannot solve or start with my solution, you should message me. Okay, you should message me. Okay, continue. Okay, so let's say your function can be split up into function in x and function in y individually. Okay, then you can split out your iterated integral. Okay, so for example, in this case here, if you want to double integrate sine x cos y over a rectangle, okay, can you see that this sine x cos y is continuous on the rectangle? Okay, because sine x cos y is continuous. Product continuous is still continuous. So you can use Fubini. Okay, so Fubini doesn't matter you use dx, dy, or dy dx. By this case here, we can do it simultaneously. Okay, because the function can be split into x part and y part. Okay, we can do it simultaneously. So let's try do it simultaneously first, and then I show you the original way. Okay, let's do it simultaneously. So we do x part and also the y part. Okay, so if we do this, what do we get? On one side, we get negative cos x over 2 from 0, and then sine y from 0 to power 2, which is what? 0 plus 1 times 1 minus. Let's say if you want to do the usual Fubini, let's say we do it on which one first? Let's do it on dx first. Then we do it on dy. So that's a cos y. So what do you see? You really treat y as a constant. Okay, so if you treat y as a constant, you actually can pull the cos y outside the integral. Okay, you can really pull the constant outside the integral. Okay, and then you do dy. Okay, but think that this number here is just another constant if you evaluate it. So you can pull the constant outside. Okay, so this is how you get this integrating simultaneously theorem here. Yeah. Okay. So let's not compute this. It's the same calculation. So what's the picture here? So the picture is like this. So this is your surface. Okay, so the one represents the volume under this surface. Yeah. Any question? So whatever we do in the past 15 minutes is just about using Fubini's. Okay, and then how to do the iterated integral. Okay, that's all. Make sure you know this skill. Go back and do the homework. Check whether you know how to uh, use what we have learned or not. Okay, next. Let's say we are not doing rectangle integration now. Okay, so let's integrate over any region. Okay, general region here. Let's call it D. Okay, so this is an island. Okay, so this is an island. But this island is bound inside a rectangle. Okay, so this island is bound inside a rectangle. So now, let's say we have a function defined on D. Okay, now we want to extend to a function defined on the whole R. What do I do? Okay, so well, this big F here could take the usual value F small f in D, but what happens in the other part of the rectangle? This function is defined piecewise as 0. Okay, so I mean, do we have the diagram? Yeah, diagram is here. So we have a graph potentially defined on D, but if I want to extend the domain, I still use the same small f. But what happened to the f value on the other part of rectangle? I just divide it to be 0. Okay, so you can easily see that if I'm gonna integrate over this general region here, it is just integrating the new f, okay, over the rectangle. Does it make sense? Make sense or not? Any question? Thank you. 我在讲什么？question 有问题吗？question。哎，绿的有问题吗？重复一下我讲什么？错问题，重复一下。Integrate the f and then 蓝色变零，水变零。not quite，not quite。这个 area 肯定还在的，它不会变零，水变零现在。So there's a small f and capital F here. Okay, so there's different f you are integrating here. Okay, so what's this capital F related to this small f here? How they are related? So this capital F defined on D is just the usual f, small f. But what happens outside D, inside the rectangle? This capital F is 0. Okay, so 你看啊，这个是蓝色，这边也是蓝色。So if you look at all the blue color as F, the F value take outside D is 0. OK 了，听得懂讲吗？来一点，重复一次。随便你 F 变零 ，before integrate 就要变零。对，before integrate 就是零的。before。Okay, so before integration is 零 ，after integration 呢，still 零啊，because you integrate over function 0 嘛。Understand? Yeah, before integration already 是零啊，因为 because this is what we have defined here. Okay, on D it is small f, outside D it is 0. Okay, yeah. So 你可以想象一下为什么我们要做这样无聊的事情吗？很无聊吗？无聊啊！一不要上，它第四方形你去上。Sorry? A B 不是啊，要一个分钟理解答案哦。喂，中午好像讲一个 我们不再讨论的东西啊，你再讲一次，慢慢再讲一次。So why? OK， 我的问题是啊，为什么我们要 relate 一个 general region 去一个四方形？这是我问题。Why do we relate a general region to a rectangle？ 对，但是为什么不要用四方形来解决？这样把四方形解决。Because previously we learned what? We only know how to integrate over a rectangle. So we need to relate it back to what we learned before. OK 吗？明白吗？之前我们 how to integrate over rectangle what do we use? We use iterated integral. Okay, we use partial integration. Okay, so we don't know how to integrate general region, but we can always turn our general region into rectangle. Okay. Okay. Okay, so let's see how we're gonna make full use of this idea here. All right. So first part. First part. Actually, we don't tell you how to go to here actually, but maybe you should go and see why is it true. But just learn calculation first. All right. So look at this. So now this is D. Okay. So this region is a not regular one. So how is it not regular? Do you know how to read this region here? So to read this region, you should tell me where this X lie, where this Y lie. Okay. So if you look at this particular picture here, where does what X span? X span from where to where? A to B. A to B. But why? Why? If you look at a single A, the Y is different. Okay, the Y is different. If you look at single A, the interval of Y is different. Keep changing. You know how to imagine this? So you should draw a straight line like this. When you can see that this interval keep changing. But it changes with a way, right? It changes with a way. So what way is this? If you look at the lower bound of all the interval, it follows a function by x. So meaning if I put a here, g1a is the lower bound here. Okay, if I put b, and g1b is the lower bound here. Okay. Similarly, for the upper bound, you also have a control by x also. So if you have this kind of region, okay, you can use this formula here. Okay, what's this formula here? You can start by integrating over where? Over y first. Okay, over y first. Because y change with x. Only then you integrate over x. Think about why this formula makes sense. Why this formula makes sense? 为什么不要做 x 现在做 y? Why this makes sense? Why this makes sense? So if you integrate over y first, you can replace all the y with variable in x, and then only then you integrate over x, so the x will disappear. Okay, no? Make sense? If you do x first, what happens? You're left with y, and then you integrate y is in terms of x, then you will left with a bunch of x. So it's not a number. Okay, so to get a number, you should integrate over y first. Okay, to get rid of the y in terms of x. Only then you get rid of x. Then you get rid of all the variables. Okay, now. Know how to remember? So here there's another ironic thing. Okay, ironic thing here is if you integrate over y, actually your y is depend on x. Yeah, so there's something to note here. Okay, so don't confuse yourself. Okay, how about the other region, the other type? So the other type is your x variable is controlled by your y. Okay, so if you fix one y slice, and then you can see that your s is keep changing. Okay, and every y your x is changing. Okay, but if it changes in a nice way with y, what do you do? Okay, what do you do if you want to do double integral from this region here? So you need to get rid your s variable first. Okay, to replace everything y. Only then you integrate over y. So get rid x and y. Okay, no? Okay, simple idea. Huh? So let's try. Okay, let's try this. Try and evaluate this iterated integral here. How about you compute first, and then later we'll try and draw this domain. Okay, I give you 2 minutes to draw it, and then we will try and we'll try and draw this domain. Actually. Okay, compute first. I'll let you compute first. Okay, do you get this number here? Do you get this number? 10180. You get it? Okay. Right. So calculation is one thing. The main thing about this last two chapters is, do you know how to draw this domain and function? Because you need to rely on your drawing to compute later on. Okay, so in this case here, how to draw this domain here? Well, I mean, you should write down your integration domain first. Okay, so you need to write down your integration domain first. So in particular, you need to tell me where x and y are bounded. Okay. So if you look at this integration domain where x bounded, you integrate from where to where? 3 to 5. Okay, how about y? Y is going from minus x to okay. Right, so let's draw this. Let's draw it. So let's take your y out. So 3 to 5 here. Okay. So what does it mean by y is from negative x to where? For example, when x equal to 0, where is y? When x equals 0, where is y? Where is y? Equals to 0. Okay, so there's only 1 point here. But when x equals to 3, it is from minus, okay, minus 3 to 3 squared is 9. Okay. How about 5? Negative 5 to 25. Okay, so if you play with all the x's, maybe I think should go higher. And then on the other side, you have a linear graph here. Well, let me draw it. Okay, so what you see here is 这边有点丑，我画一点，这样子，就带下来。Okay, so what can you see here is with different x, you have different y interval here. In particular, what? In particular, the boundary is one of the boundary upper bound is y equals to x squared. The lower one is y equals to minus x. Okay, so what's the boundary integral computing is? You look at this domain and then what is the surface at the top? Okay, what's the surface? Okay, at the top. Imagine or not? You still need another axis to draw out your surface. Okay, you should need another axis to draw out your surface. Okay. Okay. Is it clear? Yeah. Okay. If it is clear, then what? Then can I give you a task? Can I give you a task? What task is it? Can you try and change order? Can you try and change order? So meaning, you fix your y first. So you fix your y and then fix x. So y is going from where to where? Where to where? Here to here. So it is -5 to where? 35. Good. Then can you express s in terms of y or not in this case? Can you do it? So let's remove this purple stuff. Can you do it or not? Maybe you can discuss this and then we can finish. Can you express x in terms of y? So if you fix x, right? How to fix x? So fix x is going the other direction. So you fix, fix y. So y is this direction. Okay? Fair enough. So it is left bounded by these two pieces, right bounded by this line. Okay, so what's this line? Line. S equals to 5. Good. S equals to 5. But on the other side, seems like you cannot do it at one go. Correct or not? Because these two pieces of curve defined by different part, different function. Okay. So in particular, this part is what? Minus y. Okay, this part is minus y. So you need another one. What do you need? So this one we should go to 0 only. And then you need the other part because the left bound is described differently. So the left bound for y from 0 to 25 is what? Square root? Square root 1. Good. Okay, so try and add out these two integrals. Okay, do you get 1018 over 3? Okay. Does it make sense? Okay, so we split. If we do the other order, we split it into two parts. Okay, can try? Yeah, so I'll go back and try. You should get the same. Okay, any question? Any question or not? Hey, no question. See you on Monday. Friday, sorry. Friday.对啊，我的电话嘞，我电话哎，我麦。Hello. Hey, by the way, there's something to change here. where is it changing? We just compute from where to where? From 3 to 5. We just stop at 3. We don't compute to 0. Okay. Yeah, we just compute to 3. Yeah, try and change it. Let me try and fix it. If you want to do this question also can, but you need to compute another order also. You want to do this question. Okay? Yeah. Try it, yeah.
我讲你刚刚讲那个
什么？
热那种，你要问东西你看。
是等下几点？
啊？
几点找你啊？
现在啊？